Welcome to the Network Operations module. By the end of this module, you should be able to describe traditional network operations. Traditional computer networks were designed and operated as a set of individual components and services. This traditional structure was used regardless of whether the networking domain was a service provider WAN or an enterprise data center. Using a traditional approach to network operations, new customer services are implemented using manual processes, often using a device-level CLI. Implementing new types of network services requires installation of new equipment and connections. Many of today's networks lack the flexibility and scalability required to run modern applications. This means network operations becomes a bottleneck as new applications and services are brought online. And the network grows larger and more complex. Traditional network operations also rely on manual failure remediation processes that increase service downtime and negatively impact the customer experience. Changes to the way modern applications run require the network to keep pace. To deploy applications at scale, network and service configuration must be automated. Applications running in virtualized environments such as private, public, and hybrid clouds require networking to be virtualized as well. Instead of deploying and managing physical hardware devices, software-based virtual switches, routers, and firewalls are used. Modern networks are also able to dynamically adjust and optimize traffic flow based on the analysis of network telemetry data. The primary reason for changing the traditional approach to networking comes from the fact that computer networks often exist as parts of larger projects and must evolve in unison. Consider these examples. An application running in a public cloud, where large pools of compute, storage, and networking resources are being shared by many customers or tenants. Scaled web services accessed by millions of users requiring multiple tiers of a web application to be dynamically connected. A traditional telecom operator choosing to evolve their business model and become a content delivery operator. The network must be adapted to deliver different, ever-changing content. For example, video, data, gaming, and so on, to millions of subscribers. In environments like public clouds, networking may be completely virtualized and run in software. Because of these trends, networking is now being treated more like a software project, with corresponding characteristics like version control, code reviews, test before deploy, and so on. Because networks are now being treated like software, you will learn about some software development methodologies. The classical approach to software development is summarized by what is called the waterfall model. Its formal description was first given by W. Royce in 1970, while the actual term waterfall was introduced by T. E. Bell and T. A. Thayer in 1976. Based on this software development model, you first collect requirements for the new software before the software design process begins. After the design process is complete, then the design is implemented in code. Finally, you can test and deploy the new software. Each phase of the development process begins only after finishing the previous one. The waterfall model works if you know your requirements very well in the beginning of the development process. When requirements change during the development process, and a need to develop new functionality arises. The waterfall model shows some weakness. It is not the most flexible development model and requires more time before new application functionality can be deployed to production. Additionally, the waterfall model takes into account there is a significant interval of time between releases of software. Each new release contains a large volume of code changes because multiple features are typically released at the same time. This increases the probability of issues at the deployment time. Agile is an umbrella term for multiple software development practices that began appearing in the past few decades. These practices permit a much more iterative and incremental development process compared to the classical waterfall model and its variants. In 2001, leading software developers came together to create the Manifesto for Agile Software Development, stating these 12 main principles. The highest priority is customer satisfaction through early and continuous delivery of software. Welcome changing requirements even late in development. Agile processes harness change for the customer's competitive advantage. Frequently deliver working software in time frames ranging from a couple of weeks to a couple of months, with a preference to the shorter timescale. Business people and developers work together daily throughout the project. Build projects around motivated individuals. Give them the environment and support that they need, and trust them to get the job done. The most efficient and effective method of conveying information to and within a development team is face-to-face conversation. Working software is the primary measure of progress. Agile processes promote sustainable development. Sponsors, developers, and users should be able to maintain a constant pace indefinitely. Continuous attention to technical excellence and good design enhances agility. Simplicity by maximizing the amount of work not done is essential. The best architectures, requirements, and designs emerge from self-organizing teams. At regular intervals, the team reflects on how to become more effective, then adjusts its behavior accordingly. The Manifesto for Agile Software Development is available at the Agile Manifesto website. You can access the website from the reference links document. The Agile Software Manifesto formulated the main values of Agile, such as individuals and interactions over processes and tools, working software over comprehensive documentation, customer collaboration over contract negotiation, and responding to change over following a plan. Welcome to the DevOps Principles module. By the end of this module, you should be able to describe DevOps principles and benefits. DevOps is a combination of technologies, design concepts, mentalities, and ideals that enable high-performing IT teams to move quickly while maintaining stability. DevOps aims to unite development, operations, and other teams in your organization to improve communication, collaboration, and integration. DevOps creates a tight loop between product release and feedback, with the ultimate goal of decreasing the time to market while increasing organizational performance and customer satisfaction. DevOps philosophies originated within the software engineering culture, as well as within the lean manufacturing revolution that began during the 1980s. The main principle of lean manufacturing is eliminating everything in the production chain that does not help to create the final product. Using DevOps, changes in functionality can happen frequently and are moved to production quickly. Automation and orchestration play a critical role, and if errors are encountered, a system can be quickly rolled back to a known state. DevOps enables quicker integration of new software, especially software upgrades and patches. It enables developers to deliver software in smaller portions, using a faster cadence. The overall result of adapting DevOps practices is faster time to market for new functionality and an overall increase in organizational performance, product quality, and security. The DevOps practice of maintaining identical development, testing, staging, and production environments creates confidence that the new software will deploy successfully. Traditionally, networks have been managed on a device-by-device basis, deploying simple changes, such as adding VLANs to ports in medium to large networks, causes considerable strain on network operations. At the same time, compute infrastructure operators have adopted DevOps tools and processes that enable them to move quickly. DevOps aims to align technology, design, and processes, while software development teams and compute infrastructure teams have embraced these methodologies. Network operations is just starting to come on board. Junos automation solutions enable network engineers and operators to move at the rapid pace demanded by the DevOps community. Juniper embraces various automation and orchestration tools, such as Ansible, Puppet, Chef, Salt, and so on. Junos enables network engineers to use common DevOps tools for full orchestration of large-scale service deployments. DevOps brings automation to the network, resulting in increased speed, reduced cost, and a decrease in the number of configuration errors. Junos devices are completely programmable. Every capability baked into the Junos CLI is exposed to developers, making the platforms completely automatable. As you investigate automating your network, you might encounter the term Infrastructure as Code, or IAC. This term is used both inside and outside of DevOps circles. IAC is a very popular method to manage cloud-based resources because it provides complete infrastructure lifecycle management. All infrastructure is managed and provisioned using code. This generally includes deploying new virtual servers, applications, and networking, and also terminating those resources when they are no longer needed. Using code, you can create a new virtual router, switch, firewall, or any other virtualized network function or VNF. You can then configure and monitor the virtual device using code, just as you would a physical device. Virtual devices are also easy to move and duplicate when needed. This makes it possible for your development, test, staging, and production environments to be identical. Juniper's VMX, CSRX, and VSRX are examples of virtual network devices. A typical IAC workflow is shown here. Code is created and then stored in a version control system or VCS. Next, the device code goes through an automated code review process, is integrated back into the primary code branch, and is deployed. You can see how closely the IAC project workflow resembles the workflow of a typical application development project. Management of your infrastructure is now a coding project. The practices of DevOps are an outcome of its culture. Adopting the practices without the culture creates a short-lived experiment too shallow to stick. Understanding and internalizing the DevOps 3 ways principles help you develop a DevOps mindset. The DevOps 3 ways are basic principles which all DevOps practices naturally follow. They are flow, feedback, and continuous experimentation and learning. Workflows from developers to operations. Feedback is returned to the development team, and adjustments are made. Continual experimentation and learning is a frequent, reoccurring process. Welcome to the DevOps Practices module. By the end of this module, you should be able to describe DevOps practices. With any production system, there is a process flow from beginning to end. In manufacturing, the process flow begins when an order is placed and ends once the product is delivered to the customer. In an application development environment, the flow begins when a new software product, feature, or change is requested, and ends when the software, feature, or change is delivered to the customer. The goal in both manufacturing and software development is to shorten the time to deliver. One of the first things an organization can do to improve process flow is to stop doing things that are going to hurt those downstream in the production process. All participants need to understand the production flow and how what they do affects others in the organization later on. Common problems include poor documentation, sloppy code, or implementing new features without sharing that information with others in development and IT. Sometimes, a local improvement in the code or in IT operations may improve the function of an individual code module or network function, but degrade the system as a whole. Always keep the health of the entire system in mind when working on an individual part. If you have two options for doing the same task, focus on the one that increases the rate of flow in the long run. For example, it may take more time to implement automation than it takes to do the task manually. However, if you automate a repetitive task, the value of that automation far outweighs the value of getting the task done quickly one time. Technical debt is something that occurs when you implement a short-term workaround to get a product out the door. You know that you should circle back to repair the workaround later. However, because you didn't have time to do the task right the first time, it is unlikely that you will have time to revisit the workaround in the future and clean it up. Soon, you'll find that you must create a new workaround to maneuver past old workarounds. Like financial debt, technical debt also accumulates interest as time marches on. Eventually, the house of cards comes crashing down, and the piles of broken quick fixes become a source of much pain. Make sure that you give enough time to implement the proper solution initially, so that you don't enter into technical debt. Provide developers and IT operations teams with the necessary time to avoid or clean up technical debt as an anticipated part of their workload. The second way is feedback. continuously gather feedback from each stage in the flow process. You utilize this feedback to know what is working, what is not, and what needs to improve. Collect feedback from developers, operations, customers, and anyone else who may have information that can help you improve the flow or quality of the product. You can collect feedback from people, as well as from automated monitoring and measuring systems. Feedback is a primary method for identifying ways to shorten and improve the flow. Using feedback to shorten your process flow includes shortening the time it takes to collect and analyze feedback. Note that the sooner you get feedback, the sooner you can integrate positive changes into the system. Set aside time to evaluate feedback and implement improvements. Feedback, process speed, and product quality metrics should be gathered over time to determine if a flow is improving. It is also important to give time in an employee's workload to implement improvements. Some companies give up to 20% of a worker's time to implement improvements. If everyone understands that the ultimate goal is to improve the flow, participants are unafraid to suggest improvements in their own processes that could improve the system as a whole. They begin to feel confident enough to take risks and try new things that can improve the flow even further. Individuals who are willing to take the risk of innovation should be rewarded for their efforts. As much as you strive to make a system fault-tolerant, it is difficult to know just how tolerant a system is to failure until you test it. Finding and eliminating risk in a system is much easier when you are actively searching for points of failure as part of a plan to improve. Some companies purposely unplug devices or break processes temporarily to stress test a system and observe how employees and systems deal with the problem. Testing a system helps to ensure that theoretical recovery plans work when it counts. Continuous integration, or CI, is the practice of frequently committing the code to a shared central repository and automating the build and test process of the code each time someone pushes new code into the repository. The goal of CI is to provide rapid feedback. If a defect is introduced into the code base, it should be identified and corrected as soon as possible. For CI to work, a VCS such as Git is used. Some additional tools that automatically perform tests on the code might also be required. A major aspect of CI is that developers are routinely reintegrating the code with which they are working back into the primary or main branch of code in the VCS. The longer developers wait to integrate their code with the main branch, the more likely it is that there will be incompatibilities that slow the flow of production. Submitting the code for integration at least once a day is recommended. With continuous building and testing, the primary code is theoretically in a releasable state at any time. Quality compliance and security testing are performed at each step of the process. Reserving extra time for testing at the end of the process is unnecessary, since testing occurs throughout the process. Continuous delivery and continuous deployment are natural extensions of CI. These terms are often used to describe the DevOps model. The difference between the two is that continuous delivery makes sure that the code is ready to deploy at any time, while continuous deployment is a way to automate the code deployment. The most important aspect of continuous delivery and continuous deployment is that operations, security, and compliance teams are brought into the conversation much earlier than before. Being a part of the process early on enables these teams to give valuable input and visualize the process from beginning to end. Depending on the size of your organization and the exact field of activity, DevOps principles can be implemented differently. Google's Site Reliability Engineering, or SRE, started as a software engineer's way to manage repetitive tasks and is now an extended set of principles, practices, and incentives, which helps to manage large and complicated services at scale. One can view SRE as a specific implementation of DevOps with some extensions. DevOps can also be thought of as a generalization of several core SRE principles to a wider range of use cases. Network Reliability Engineering, or NRE, can be thought of as a DevOps implementation for networking. It has its own specifics, and yet still uses many of the common DevOps ideas, approaches, and tools. Traditional network operations are a bit like firefighting. with fire disguised as randomly appearing network failures that require manual intervention to resolve. NREs employ DevOps principles to ensure reliable network operations. It focuses on customer satisfaction and service availability. Networking is inseparable from connected systems and applications. NRE embraces failure as a way to ensure the same error does not happen again, relies on proactive testing, and is a continuous journey. The main NRE behaviors can be summarized as codify, beginning with the acquisition of network software and hardware systems, commonly called Day Zero. An NRE codifies the network software artifacts, secrets, and configuration into source code repositories similar to a software developer. Automate, using a DevNetOps pipeline. An NRE automates development, testing, staging, and production deployments. NREs use this pipeline to provide reliability, scale, efficiency, and optimization for dynamic provisioning of networking resources for its consumers and systems integration. Test. Through automation, staging, and stress testing, an NRE ensures that the deliveries are reliable enough to meet service level objectives and agreements. Monitor. An NRE monitors service level indicators, both manually and automatically, and using analytics, triggers automatic responses and alerts for anomalous and statistically meaningful events. Logs and telemetry are collected and analyzed to derive insights used to optimize network performance. Measure. The NRE culture values truth and transparency and uses indicators to measure their effectiveness in meeting reliability goals, such as mean time between failure, or MTBF, and mean time to resolution, or MTTR. Improve. Permanently improve the stability of the system, visibility, and incident reaction time. Network DevOps is the application of DevOps philosophies, principles, and behaviors to network operations, or NetOps. Network reliability engineers put it into practice. DevOps principles counter the waterfall methodology, where extended planning, building, and testing cycles occur in long sequential stages. Research has shown that for the IT and manufacturing industries, smaller and more frequent deployments result in improved operational speed, agility, and quality. By working in shorter and faster cycles with smaller deployment deliverables, a network DevOps pipeline reduces the time between design changes and production deployment. All network changes go through the same pipeline to ensure consistency. Although the stages can vary in different implementations, the network DevOps pipeline stages are common. In the design change stage, the network architects and engineers, based on business needs and customer feedback, decide what change is needed in the network. In the commit change to VCS stage, the change, in the form of code, is committed to a VCS. In the notify and peer review stage, the team is notified of the proposed change, and team members review and approve or reject the change. In the automated testing stage, the tests run automatically, ideally in separate testing and staging environments. In the automated deployment stage, the change is deployed or committed to production. The team is notified about deployment success or failure. Failed deployments can be rolled back. In the continuous monitoring stage, the network telemetry is collected and analyzed to provide real-time network performance indicators. The telemetry is compared to service level indicators and is used to make reactive or proactive adjustments to the network. Finally, in the continuous improvement stage, the failure is viewed as an opportunity to improve. Feedback is encouraged and is used to optimize the overall system performance. DevOps advocates a specific culture and suggests practices that emerge as a result of that culture. It does not recommend specific tools. These are some popular tools used for various development processes. The selection of tools varies depending on the use case. A few tools are selected to demonstrate how DevOps practices can be used with Juniper software and hardware platforms. Each tool represents one of many that could be used for a particular task.